Hey everyone, and welcome. Today, we're going to dive into a concept that completely changed the game for software development: object-oriented programming, or OOP for short. It's a really cool way of thinking that teaches computers to handle complexity by, well, acting a little more like we do.
So let's just start with a question to get our heads around this. How in the world would you teach a computer to think about a car? I mean, a car has a color, a model, it can speed up, it can slow down, it can do all sorts of things. How do you capture all of that in code? It's not just a list of data, right? It's a thing. And that is exactly the puzzle that OOP was created to solve.
And the solution is actually pretty brilliant. Instead of just writing a massive, long list of instructions for the computer to follow from top to bottom, object-oriented programming says, hey, let's build our software by creating little digital versions of real-world things. It's a whole way of programming that's built around these little self-contained bundles, which, funny enough, is kind of how we naturally see the world anyway. All right, so to start building our virtual car, we need to get a handle on two really basic ideas. These are the absolute cornerstones of OOP. It's really just about the difference between a plan and the actual thing you build from that plan. First up is the object itself, the O in OOP. In this world, an object can be literally anything. Your phone, that's an object. You're an object. And our car, of course, is an object. Now, every single object has two parts. It has properties, that's the stuff about it, like the car's color or its price, and it has behaviors. That's the stuff it can do, like accelerate, brake, or honk the horn. Okay, so if we have an object, where does it come from? Well, you can't just wish a car into existence, right? You need a design plan, a blueprint. In OOP, that blueprint is called a class. A class is what lays out the whole structure, defining all the properties and all the behaviors that any car made from that blueprint is supposed to have. So, now that we have our blueprints and we can create our objects, you can imagine things could get complicated really, really fast. The next few principles we're going to talk about are all about managing that complexity. It's about making our virtual car way more user-friendly and a lot more secure. And the first idea here is something called abstraction. Now, it's a fancy-sounding word, but you use it every day. Think about driving a real car. You just use the steering wheel and the pedals, right? You don't need to know or want to know how the engine is firing or what the transmission is doing. That's abstraction. It shows you only what you need to see and hides all the messy, complicated stuff under the hood. And right alongside abstraction is encapsulation. So if abstraction is the simple dashboard you interact with, encapsulation is like the sealed metal casing around the engine. It's what bundles all the engine's important internal parts, the data, together with the code that makes them run, and it puts a protective shield around them so nobody can just go in and mess things up. Let's make sure we've got the difference clear, because they can sound a little similar. Abstraction is all about making things simpler for the user by hiding how something works. Encapsulation, on the other hand, is all about security. It's about protecting what an object works with, its internal data, for being changed when it's not supposed to be. One's for simplicity, the other's for safety. Okay, so this next idea brings us to one of the biggest, most powerful advantages of OOP. I mean, once you've gone through all the trouble of designing a really great blueprint, you shouldn't have to start from scratch every single time you want to make a slightly different version. And with OOP, you absolutely don't have to. This is where inheritance comes in, and it's a huge deal. It's a way for a new class to just, inherit all the properties and behaviors of a class that already exists. This is massive for code reusability. Car manufacturers do this all the time. They don't invent a whole new car from nothing for every single model. They take a basic, proven platform and build on top of it. So let's picture it. We have our blueprint for a basic car. This is our parent class. It's got all the normal stuff: 4 wheels, an engine, it accelerates, it brakes. It's just a solid, standard, generic car blueprint. Now this is where the magic happens. We can create a totally new blueprint. Let's call it a sports car that inherits from our basic car blueprint. And just like that, bam! It instantly has 4 wheels, an engine, brakes, everything. And then we can just add the new special features, like a turbocharger or a spoiler. We just reused the old design and added our upgrades so much faster. All right, we've made it to our final core concept. And you could argue this is one of the most flexible and, frankly, mind-bendingly powerful ideas in all of programming. It's called polymorphism.
I know, the word sounds super intimidating, but let's just break it down. It's from Greek. Poly means many, and morph means forms. So polymorphism literally just means many forms. In programming, it's the amazing ability for a single action or command to have totally different results depending on the object you're using it on.
For instance, let's say we have one simple command, start engine. Now, if we use that command on our regular car object, we get a nice, loud vroom. But if we use that exact same command on an electric car object, we just get silence. And what if we use it on a boat object? Maybe we get a splutter splash. See what's happening? It's one command, but it results in many different, totally appropriate behaviors. That right there is the magic of polymorphism. So, we've covered a lot, right? Classes, objects, and these 4 big principles: abstraction, encapsulation, inheritance, and polymorphism. Which brings us to the most important question of all. So what? Why does any of this matter? Why was this way of building software such a revolution? Well, it all comes down to these huge benefits that really enabled us to build the incredibly complex software we use today. Inheritance means we're not constantly reinventing the wheel. Encapsulation gives us much better security, and because everything is a self-contained object, maintenance becomes a dream. You can fix or upgrade one part of the car without worrying about the whole thing falling apart. But maybe most important of all, it lets us write code that actually reflects the real world, which makes it so much easier for us humans to understand, build, and grow. The really cool thing is, once you start to think in terms of objects, properties, and behaviors, you start to see these blueprints everywhere. The whole world is just full of these amazing systems that are waiting to be modeled. So I'll leave you with this thought. Now that you see the world as a collection of objects, what blueprint would you design first?